Well, thank you, Lars, and thank you, everyone, for coming. It's nice to see so many of you here. So this award provides a nice occasion for giving this lecture, but also what makes it an especially nice occasion is that the things I'll be talking about are very lively right now, and that's because of work that was done here at the KITP. So I'm going to be talking about physics under extreme conditions. And so to start, to orient ourselves, I'll start by talking about physics, about everyday physics, physics that we all sort of learn as we grow up. We learn what happens when we throw a ball, when we slide down an inclined plane, when we boil water, when we play with a magnet. And this is physics on a human scale measured in meters and kilograms and seconds. But in fact, a lot that we learn on this scale also works as we go to much smaller scales, much larger scales, faster scales. But as we push to the extremes, as we look beyond what we can just see on our own scale, we find in several directions new physical laws and new phenomena that are contrary to our experience and that seem strange at first. And there are really three such directions: the very fast, the very small, and the very massive. So in particular, if we look at things that move very fast, close to the speed of light, we encounter the strange things that happen with special relativity. Clocks that are moving close to the speed of light slow down. Measuring sticks and other objects that are moving very fast shorten. And mass and energy can convert into one another. So that's the very fast. When we get to very small, there's a different kind of strangeness, quantum mechanics. And so, for example, light behaves both as a wave, as in that picture, and as a particle, as in the famous photoelectric experiment. And not just light, but electrons also behave as waves and particles. And in fact, all of the things that we normally think of as forces and as particles have this dual nature, sometimes behaving like waves, sometimes behaving like particles. Also, in quantum mechanics, it can really be in two places at the same time, as in this directory from the Institute for Quantum Physics, which says you are here, or maybe you are here. So that's the very fast, the very small, and the last extreme is the very massive. Very massive objects actually cause space and time to bend. And this is what we perceive as gravity, but what it really is, the best explanation is again the bending of space and time. Not only that, but space can itself expand. The universe is expanding. And massive enough objects will collapse into black holes, which are so dense and have such a powerful gravitational force that nothing, not even light, can escape from them. So these are the new things that happen in the very massive regime. So each of these three extremes, very fast, very massive, and very small, is the arena for one of the great theories of physics: special relativity, general relativity, and quantum mechanics. These were the three revolutions in physics from the last century. And each of these theories is now tested very, very well. And these three theories provide for us still the basic framework for our understanding of space and time and matter, and even in quantum mechanics, reality. Of course, these are all about 100 years old, you'll notice. Long time. But the good news for those of us who are still working in the field and want to do something interesting is that these revolutions aren't complete. We know that. Because if you think about it, discovering these three new theories really opens up three new questions. We've understood the very fast, the very massive, and the very small, But for example, what if an object is both very fast and very small? What if we have to deal at the same time with both the strangeness of special relativity and the strangeness of quantum mechanics? And that's a very good question. That's a very deep question. And the first person to address it was Paul Dirac, who answered it. And as an unexpected bonus from answering that question, he made a new discovery, the existence of antimatter. He found that every particle had a partner. The negatively charged electron has a partner, the positron. And one of the properties of antiparticles is when they get together with the ordinary particle, they can annihilate into a flash of light. So I want to say a few words about how Dirac did this, because I sort of want to explain to you a little bit about how theoretical physicists work. OK, so this is Schrodinger's equation from quantum mechanics. Now, this is a public lecture, and you're not supposed to have equations. So think of this as a piece of art. But this particular piece of art is very useful. It explains the properties of atoms and molecules and chemistry to high precision. But it can't be complete because it doesn't work for particles that are moving close to the speed of light. It doesn't incorporate the relativity principle. So it's fine for slow particles, but it can't be the complete story. And so Dirac set out to find a better equation, so this is called the Schrodinger equation, by the way. And Dirac set out to find a better equation, which would have all the successes of the Schrodinger equation for slow particles, but would correctly incorporate special relativity for fast particles. And he succeeded. This is the equation that's named for him. And it does what he expected. It reproduces these successes. It's in accord with special relativity. And it gives a more precise account of the behavior of atoms and molecules and so on. But he got an unexpected bonus from this. Because when you sort of look at all the solutions to this equation and all the solutions to this equation, this one has twice as many. It has the ones he expected, which were just the improved versions of the solutions to this one, and then another set, equally many, where did they come from? What were they there for? And after puzzling over this for a year or so, he realized that the extra solutions were, in fact, describing a new particle, the positron, the antiparticle of the electron. And so he predicted from the existence of antimatter. That was in 1930, and in those days things moved very fast because this confirmation was confirmed by this prediction was confirmed by Anderson 2 years later. Anderson was looking at particles produced by cosmic rays, by collisions of high-energy particles from supernovae with our atmosphere, and this is a track produced by a charged particle in his apparatus, and from the direction of the bending, it's bending because it's a magnetic field, from the direction of the bending and the rate of bending, he inferred that it was about as massive as the electron, but had the opposite charge. It was a new particle, and it was the one that was predicted by Dirac. So that was a very fruitful question, but that wasn't really that wasn't the end of the story. This problem of unifying special relativity and quantum mechanics went on after Dirac. It actually required that we develop a sort of a whole new mathematical language, quantum field theory. And this unification was also the key to formulating the Standard Model, which is the name given to our basic theory of matter. The Standard Model was formulated around 40 years ago. And just as Dirac predicted a new particle, the Standard Model predicted, well, depending on when you start counting, 5 new particles. And one by one, they've been discovered. The gluon, then the W and Z bosons, then the top quark, and just this past year, the Higgs boson. Now, putting together the Standard Model was a bit more involved than what Dirac had to do. Dirac really just had to do what I described on that one slide, To understand the Standard Model, it required additional experimental data. It required additional theoretical ideas. But really, the fact that this theory had to incorporate both special relativity and the quantum principle was a very strong constraint on what it could be. It really is it's the reason why one could find this theory with such precision and predict 5 particles, predict their detailed properties, and get it right. So this is a fantastic example both of humans' ability to figure things out and also their ability to go and, in the end, do the experiments, because these were heroic experiments to discover these particles. And it's worth mentioning that physicists at UCSB played major roles both in the theory side and in many of these discoveries. So, the problem of the very fast and the very small together has been a very fruitful one. But there's 2 more pairs to consider. What if an object is both very fast and very massive? And that turns out to be an easy one, because when Einstein first wrote down general relativity, special relativity was built in, so he answered that all at once. The interesting pair, the one that we're still, the one that this talk is about, the one that we're still so puzzled by today, is what happens if an object is both very small and very massive, or all 3, small, massive, and fast. And this is the problem of quantum gravity. Quantum for small, gravity for massive. Now, you might ask, isn't this a contradiction? Can something be both very small and very massive? And so I'll mention some places where this can happen. First of all, it can happen in particle collisions at extremely high energies. So particle physicists like to bang particles together. And I'll be saying more about this later on. But if you collide them hard enough, you will get into this regime where, again, you have both the very small and the very massive. A second place where this comes up, so the universe we know is expanding. If we follow it back in time, it was becoming smaller and denser. And in fact, observationally, one can follow this back remarkably far. To a time when the universe was vastly smaller and vastly more dense than it is today. Very close to this regime of quantum gravity where both quantum mechanics and general relativity, the small and the massive, are acting at the same time. And as more precise observations come up, we get closer and closer to that regime. So understanding the unification of our theories of the small and the massive is also a key to understanding how the Big Bang began. And finally, there are those black holes that I mentioned. And if you follow the black hole to its final fate, it ends up, as far as any theory we have now, crunched down to a point. And so you have there something which is truly massive and small. And so here are 3 places where you have to worry about both of those theories at once. Now, all of these experiments or regimes are very far. All of these things I've described are really very far from direct experiment. Maybe it's getting closer with the early universe, but they're still really very far from direct experiment. And so to do what we want to do, we have to rely heavily on theoretical reasoning the way Dirac did. Now, I described what Dirac did, and what it sounded like and what it basically was, it sounded like he sat around fiddling with equations. And you might imagine that that's what a theoretical physicist does all day, sit around and fiddling with equations. And it's sort of true. But Dirac was an especially pure physicist in many ways. He was very mathematical. And there are other kinds of reasoning that are very useful. And I want to talk about a particular kind of reasoning which is extremely valuable, known as a thought experiment, which has been employed by many people. And to illustrate what this is and how it works, I want to tell you about my favorite thought experiment, which is the one that James Clerk Maxwell used to figure out the laws of electromagnetism. So here are more equations, but it's OK because they're on a T-shirt. And these are the equations when Maxwell was done. But when he started, he had something less than this. So I've covered up, you'll see, one term and the bit about the light. So this is the equations as they came to him. And these equations were discovered, by and large, in experiments. In fact, they each have a name. These terms on the right each have a name. This says that electric charge. So these are the equations that describe the behavior of electric and magnetic fields. So this term says that electric charges make electric fields in a certain way. And this term says that electric currents make magnetic fields. And this term says that there's another way to make electric fields, which is if you have a magnetic field and it's oscillating or changing in time. And again, these are all found experimentally. They agree with the data. But there's something wrong with these equations as they stand. They actually don't make sense if you push them far enough. And so Maxwell exposed this with a simple thought experiment. Here's the thought experiment. It's a simple circuit. So you've got a battery, and a wire, and a switch. And then you have a break in the wire and so a couple of plates, capacitor plates. So you have a break in the wire with a couple of metal plates at the break. And the experiment is, first of all, just to close the switch. And when you close the switch, the battery starts pushing on the charges, and the current starts to flow. And at the gap here, they can't cross over, and so they pile up for a little while at those plates. OK, so the experiment is first to close the switch, and then to measure the magnetic field at that x there. And the problem is, if you do that and you try to use the equations that were there before Maxwell, you don't get a sensible answer. You can solve them in two different ways and get two different answers for the magnetic field. So there is something wrong with those equations. This thought experiment exposes it, and with a little bit of trial and error, and actually more than that, with a certain amount of sort of modeling and guesswork, Maxwell figured out that he could fix them by adding in one more piece. And now these equations are all perfectly consistent. And he got, as Dirac did, an unexpected bonus. Because he set out to explain the laws of electricity and magnetism. And there's this law that says a magnetic field can produce an electric field. And there's this new law of his, which says that an electric field can produce a magnetic field. And so now you get one producing the other. You get not a chain reaction, but you get an endless wave, in fact, of electric and magnetic fields. And when you solve these equations, you find that wave moves at the speed of light. And suddenly he realized that he understood the nature of light, which he hadn't set out to do at all. It just popped out of his understanding of electricity and magnetism. Not only light, but this also predicts the entire electromagnetic spectrum, which was at that time unsuspected, from radio waves on up to X-rays and gamma rays. So when I heard about this, when I learned about this, I thought this was pretty much the greatest thing ever to understand the nature of light by this kind of reasoning. And I said, that's what I want to do. And I still feel that way. Now, you might ask, why was this a thought experiment? Why wasn't this a real experiment? Well, there's a good reason. Because in order to actually measure that term, you would have to actually open and close the switch very fast. You would have to open and close the switch in about a billionth of a second, a nanosecond. And you can imagine that was rather hard to do. And so this was not discovered experimentally. It was discovered by the kind of reasoning I described. 25 years later, Heinrich Hertz figured out how to open and close a switch on a nanosecond time scale and confirmed Maxwell's equations. OK, so that's the nanosecond time scale. Now, to probe quantum gravity, to probe it directly, one has to get to the nanosecond time scale. Now, how do we know that? Well, we know that as follows. I told you there are these three theories, these three revolutions. And each of these revolutions comes with its own constant of nature. So when I say special relativity sets in when things move very fast, you can ask how fast? Well, close to the speed of light. So c here is our notation for the speed of light. That's one of the basic constants. For quantum mechanics, it operates when things are small. How small? Planck's constant tells you how small. And finally, gravity, very massive. How massive? Newton's constant. The gravitational constant tells you how massive. So each of those three theories comes with a constant of nature. And now, it turns out, if you want to construct a time, if you want to construct something, if you want something which is measured in seconds, there's a unique way to combine these three constants. Here it is, kind of funny looking, but that's what it is. There's a unique way to combine these three constants to get something that you would measure in seconds. And when you do that, the number of seconds, the scale of this theory is, again, a nano to the fifth second. So this is the kind of reasoning that tells us that just as that we needed nanoseconds to test Maxwell's equations, we need 5 nanos to get to quantum gravity. Now that's 2 nanos too many. The LHC can get to roughly a nanosecond. So our most powerful particle accelerator, which has been operating in Geneva for the last few years, probes physics at roughly a nanosecond. So much better than Hertz, but still well short of what we need for quantum gravity. And so once again, we're going to have to rely on thought experiments. And there's a reason why this might be a profitable way to proceed. And to explain this, let me go back to Maxwell and think about why he was able to succeed. Why was he able to complete these equations without experimental data, but just by theoretical reasoning? Well, it was really because the experimentalists had already did most of the work. They'd found 3 of the terms. He just had to figure out the 4th one. Actually, it's a little bit harder than I made it look here, because the way I've written these equations is the way we write them today. 150 years ago, there was much less sense of how to think about these things. The equations were written in much longer and messier forms, and it was really much less obvious what their content was. So it wasn't quite as simple as just writing that. But really, the way you see, thought experiments are very useful if you have most of the picture and you're just trying to fit in the last few puzzle pieces. They help you figure out. This is one of the times they're useful in other ways as well, as I'll talk about. But one of the ways they're useful is if you already know a lot and you're trying to fit the things that you know together. And in some ways, that's where we are in quantum gravity. We have quantum mechanics. It's a very well-tested theory. We have general relativity, another very well-tested theory. And so using thought experiments, I told you about these extreme regimes where quantum mechanics and gravity both operate at the same time. By thinking about what happens in these regimes, we can, as with Maxwell, figure out where the 2 theories don't fit together, where there is something missing and we have work to do. And so that's what we're trying to do. And it seems to have been a profitable way to proceed. So for the rest of my talk, I will be telling you about, 3 kinds of thought experiment. First, high-energy scattering, strings in a box, and finally, quantum black holes. So as I mentioned, particle physicists like to crash particles together to see what's inside. This is how Rutherford found the nucleus inside the atom by colliding alpha particles with atoms. This is how quarks were discovered at SLAC by colliding electrons with protons and neutrons. It's an effective thing to do. And so, again, the LHC is doing this, but they're 2 nanos too short. So we can simply ask what would happen, given our existing theory, what would happen if they could reach the 5 nano energy, the Planck energy, where gravity and quantum mechanics come together. And so you can take the existing theories, you can start to calculate, and things look kind of good at first. And then you calculate a little bit further, and you get nonsense answers. You get infinite answers for the rate of scattering, just things which don't make any physical sense. And actually, this really wasn't a new problem for quantum gravity. It's actually not hard to write down sensible-looking equations that don't have sensible solutions, that really give you nonsense answers. And actually, on the way to the Standard Model, in understanding the weak nuclear force and the strong nuclear force and quantum electromagnetism, this same kind of problem of nonsense answers arose each time and was a valuable clue to the final form of the theory. In this case, many things were tried, and something odd seemed to cure the problem, and it was the only thing that has been found to date that cures the problem. So our existing theories are based on the idea that particles are basically perfect points. And in this is a lot of the source of the problem. And so at some point, for interesting historic reasons, people said, well, suppose they're not little points. Suppose they're little oscillating one-dimensional objects, loops. And they did the calculation, and they found that the infinities went away. It gave you sensible answers, even for scattering up here at the Planck energy, where gravity and quantum mechanics come together. Now, this is a strange idea, and it's not that everybody immediately said, oh, that's a great idea. There was about 10 years when there were roughly 3 people in the world working on this idea. But eventually, around 1984, enough good results piled up that it really did solve this problem, and that it did other nice things that you'd want a theory to do, that people started taking it more seriously. It became, as it is today, what seems like the most promising idea for unifying not just gravity and quantum mechanics, but also everything, our understanding of matter as well. So that's the first thought experiment, high energy scattering, and that's the apparent lesson of that thought experiment, that the fundamental objects are not points, but strings. Here's a second thought experiment. So going from points to strings was a big step. All of us, learned, when we learned physics, we learned the mathematics of points. And now these loops were new things. We didn't have intuition for them. We didn't know how they would behave. And so one of the purposes of thought experiments here is to just become familiar with what these new objects do, how they behave. So taking the mathematics of them and applying it in various situations to see what they would do, and in that way build up the same kind of intuition for strings that we build up for ordinary objects just by growing up with them. And there's one particular thought experiment that was very fruitful, which is to imagine a string in a box, basically in a finite space. You can imagine that space is, instead of going on forever, it closes back on itself, so it only has a size. And now we make the size smaller and smaller. And the question is, what happens when we start to squeeze the box down till it's smaller than a string itself? And the mathematics of strings gives an unambiguous answer, but it takes a certain amount of insight to figure out what the answer means. And when people figured this out, they realized that what was happening was as the original space was disappearing, was being squeezed down to nothing, a new space emerged. And again, this initially, well, this is as with Dirac, finding the right equation and then figuring out what the other half of the solutions meant. This is what the mathematics says, and then you figure out what the physics is. And so there's a couple of slogans or lessons that go with this picture. One of them is that space is not a fundamental thing. It's emergent. It comes out of something more fundamental. Because here the original space is gone, and somehow a new space has appeared. Another lesson is that there's a minimum size, a minimum distance, because if you try to make a space smaller than a string, you fail. Somehow the stringy geometry prevents you from doing this. Now, that was for a closed string, a loop of string. But there's other kinds of string. There are strings which, instead of forming closed loops, have ends that flap around freely. So closed strings and open strings. And you can take an open string and put it in a box and scrunch the box down smaller and smaller. And again, when it gets smaller than a string, you can look at the mathematics and ask, what is the physics that goes with this mathematics? And again, a new space emerges, but it's more complicated than the space before, because in addition to, it's not just an empty space, an empty box as before, it has this membrane in it. I call it membrane. I call it a membrane because it's not rigid. It can move, it can wiggle. And so the space that emerges has this object in it, which must be part of string theory. We didn't know it was there. We discovered it via this thought experiment. It's a membrane, and because of the mathematics of it, it's named for a French mathematician, Dirichlet membrane, or D-brane for short. This actually is something that I had a lot to do with. And I told you that I wanted to be like Maxwell and use the same. And in some sense, I succeeded in a small way here. I found not the last term in the equations that fits everything together, but in some sense, one additional term, one additional piece of the puzzle. And this piece tied together many things that hadn't been known to be connected, in particular, the properties of black holes in quantum mechanics, which is what I'm going to come to next. So for the purpose of this talk, this is what a black hole looks like. So this is the fate of very massive objects. You get a massive enough object, its gravity wants to pull it together, and past a certain point, it will start to collapse, and nothing can stop it. It's in the nature of general relativity that once that collapse starts, nothing can stop it. The star will crunch down to something which is as small, basically a point. So first of all, I told you that gravity is the bending of space-time. And so what you're supposed to intuit from this picture is that in this case, we have an extreme bending of space-time. There's this singularity where the star went, where the density, well, I say infinite only because Einstein's equations say it's infinite, and we don't know the right equations, so it's as close to infinite as we can tell. But there's another important place on this picture, which is the horizon, the point of no return. So the thing about black holes is light can't escape from them. And basically, once you're past this dashed line, that's the point of no return. Once you're past this dashed line, nothing can get out. Even light, you could be sitting here with a flashlight, shining the flashlight upwards, and in fact, you and the light would be falling downwards towards the singularity faster than the light could escape, and so even the light would end up not going up, going down into the singularity. So if one person if I'm sitting out here and I send my graduate student into the black hole, and they're sending me flashes of light. Everything's OK, everything's OK. As they approach the horizon, those flashes will get slower and dimmer and slower and dimmer. But once they pass the horizon, they can't get any kind of message to me. Again, it's the point of no return. Now, the singularity, you see, is a very dramatic place. The mass and the curvature is infinite. The horizon is not a dramatic place. Everything is very smooth there. It's just where the geometry has finally gotten steep enough that you can't get out. So it's very smooth, but it's just the point beyond which you can't climb out, the point of no return. Okay, that's a black hole. Now, I told you that we're trying to understand the very massive and very small. And the very massive and very small is right there. But actually, there is very interesting quantum mechanics and quantum gravity at the horizon. And that's where, in fact, most of the action that we're going to talk about takes place. So in quantum mechanics, basically in quantum mechanics, if you look on very small scales, things are jiggling around all the time. Again, they're in several places at once. And if you look at empty space, you look at the vacuum on very small scales, it's a very busy place. And one of the things that's happening is that constantly particles and antiparticles, pairs, particle-antiparticle pairs, like an electron and a positron, are popping out of the vacuum, traveling a little distance, and then disappearing again. And this has indirect effects that we can test looking at the precise properties of atoms. This affects the behavior of atoms in the neighborhood when this happens. But now I want to think about this process near a black hole. Here's my black hole again. And this is happening everywhere all the time. It happens out here, and it's fine. It happens here, it's fine. But when it happens near the horizon, sometimes, instead of the two particles just traveling a little ways and then annihilating and disappearing, one particle falls in to the singularity. One particle gets stuck on one side of the horizon and falls into the singularity, and the other escapes to infinity. And so if you're sitting outside the black hole, you now see something happen. You see particles escaping. You see that the black hole is radiating. And this was one of the discoveries of Stephen Hawking, that black holes radiate. And, well, without quantum mechanics, black holes can only get bigger. When something falls in, it falls to the bottom. The black hole has gotten more massive. But with quantum mechanics, there's this process, Hawking radiation. And if you wait long enough and don't disturb the black hole, eventually it will radiate away all of its mass, and space will be flat again. And all you'll have is these outgoing particles, whatever they are, photons, any kind of particle that the black, basically all kinds of particle will be produced by this process. Now, for astrophysical black holes, for the black holes that we've seen out there, which are as big as stars or as big as 1 million stars, this is an extremely slow process. This won't happen over many lifetimes of the universe. It's even too slow to observe. But for the purpose of thought experiments, for the purpose of thinking about how gravity and quantum mechanics come together, this is a fantastic system. And so I'm going to talk about there's not just one thought experiment here. There's many intertwined ones. And so I'm going to talk about sort of 3 eras. I'm going to talk about the 1970s, when a number of puzzles first appeared. The 1990s, when they were partly solved. And then what we're confused about today. OK, so 1970s. So Hawking and others, including Jacob Bekenstein, identified a couple of puzzles about the quantum behavior of black holes that are connected to things that I told you about. And it involved both the Hawking radiation and also, again, thought experiments, throwing things into black holes, interacting with them in various ways, watching what comes out. So the entropy puzzle is this. OK, so black holes are emitting all these particles, as Hawking said. And when you study this and when you study other properties they have, what you find is that the black hole effectively has a temperature. It's not cold. It can't be at absolute zero. It has some kind of temperature that's associated with the Hawking radiation. Now, one of the things that is familiar is that heat comes from the motion of atoms. And so if a black hole has a temperature, then it should have some kind of atomic structure, some kind of microstructure which is in motion. And that's a kind of a hand-waving argument, but it's true. There's a more precise version of it. That's what the entropy puzzle is. The entropy puzzle is that a black hole looks like this smooth and static, unmoving geometry, and yet the fact that it has a temperature says that in fact, it's not obvious here, but somehow there should be an atomic structure. There should be some kind of constituent, some kind of building blocks that are making this thing up, and that are in some kind of constant motion. That's the first puzzle. And the second puzzle from the 70s is the information paradox. So this is this process I've described, where black here's emit radiation and disappear, destroys information. So here's a cartoon of throwing a book into a black hole. The book falls past the horizon. Once it's past the horizon, nobody can read the book. You can't get out. Information can't get out. And so whatever happens later doesn't depend on the book. It doesn't matter whether we threw in, this is Stephen Hawking's book, A Brief History of Time, or we could have thrown in my book on string theory, or we could have thrown in a rock. It wouldn't matter. The radiation would be the same. By the way, OK, and this is Hawking's argument, by the way. And now this is bad. This is bad. This requires a modification of quantum mechanics. So I showed you a couple of these equations that come with quantum mechanics. And they have the following property. They can tell us that if we start with this and we sort of wait, they can tell us what the system will do as it moves forward in time. They can tell us that if we start with this and wait a while, we end up with this, with some pattern of these outgoing particles. But the equations that come with quantum mechanics have the property that they run in both directions. If I tell you that this is what I have at the end of the day, with ordinary quantum mechanics, we can run the equations backwards. And if we can do that, we can figure out which book we threw in. So what Hawking was saying was that you had to change the laws of quantum mechanics, and you had to change the nature of the equations. So instead of being able to run them back and forward, they actually lost information. They didn't keep track of what went into the black hole. Now, equations like this, equations that you can't run in both directions, are a lot messier, a lot uglier than the two-way equations. And it's kind of hard to imagine that those are fundamental to nature. And they lead to lots of problems. And so, and also, we do encounter these kind of equations in our day-to-day physics, but we encounter them not as fundamental equations. We encounter them as approximate equations when we describe a system in some kind of coarse way and don't keep track of everything. So a very strong reaction to Hawking's claim was, no, you just haven't kept track of everything. It's not that the black hole destroys information. In your calculations, you just haven't kept track of the information carefully enough. And that argument sounds good, but black holes have this horizon. And once something is past it, once some information has gotten past it, to get out again, it would have to travel faster than light. And so this information paradox of Hawking was a sharp conflict between quantum mechanics, which requires two-way equations, and relativity, which says you can't go faster than light. And it bothered us for decades. So that was the 70s. The puzzle about the atomic structure of black holes, and the puzzle which one is going to give way, or what's the resolution to this claim of Hawking's. So in the 90s, as we understood string theory better, a number of these puzzles were answered. In particular, Strominger and Vafa, Strominger was here at the time, showed that these D-branes that I told you about provide the predicted atomic structure of black holes. They imagined a thought experiment, again, in which you kind of dial the strength of gravity. And you can turn it down. You can make it weaker and weaker and weaker until you can sort of make the black hole not so black and see what's inside it. And this is what they found. Building on this, understanding better this connection, Juan Maldacena found something which was completely surprising to us, which is that you can actually build quantum, understanding how this picture and this picture could describe the same thing. He found that you can actually build a theory of quantum gravity, the kind of thing that we're trying to understand, out of the ordinary forces, out of the same kind of forces that we have, out of, say, forces like the nuclear force. This is known as ADS-CFT duality, and it is the deepest thing we know about, at this point, the bottom of theoretical physics. Again, I told you that the goal was to be like Maxwell, to follow the clues that we have and find unexpected connections. And what Maldacena did is very Maxwell-like, because gravity is this strange theory about the bending of space-time, and the other forces seem much more familiar and not so exotic. And gravity has black holes and expanding space-time, but secretly they're the same thing. And so this was a remarkable discovery. And there's a corollary to this discovery, which is that information can't be lost, because we know that ordinary forces don't destroy information, and so it had better be that quantum gravity doesn't destroy information either. So Hawking was wrong, and he actually conceded in 2004. But really, that deserves an asterisk, a very big asterisk, because Hawking's claim really is what led to this whole discovery. He made this audacious claim that quantum mechanics broke down, and broke down in a very ugly way. And it was so audacious that people had to think about it and find the mistake. And the mistake wasn't anything subtle. In fact, we still don't know exactly where the mistake was. But in understanding the fate of the information, we were led, Maldacena in particular was led to discovering this connection. So D-branes as atoms, this gravity from the other forces. And there's one more thing which comes out of this, which is the holographic principle, which was kind of predicted before Maldacena, and Maldacena's theory fits it perfectly. So in a hologram, you have a three-dimensional image which is encoded in a two-dimensional plate in a very complicated way. So all of the information to reconstruct a three-dimensional image can be encoded in a plate that has one dimension less. The construction of quantum gravity that Maldacena found is holographic in the same way. To construct this space here, the basic variables you use, the things that appear in the equation, the fundamental things, they don't live in this space. They live on the boundary, this green line. So it's the same thing. A lower dimensional description is encoding the full physics of some higher dimensional space. And for quantum gravity, it seems as though this is how things have to work, that instead of having sort of that the fundamental things are objects and fields at points, they're really projected on the outside of the space in the way that this picture describes. That's the holographic principle. Now, this is sort of where we are now. We have this connection of Maldaceni's. We have this idea that, that to construct a theory of quantum mechanics and gravity, the underlying idea is this holographic principle where things really aren't local. They aren't like other parts of physics. And we still have to figure out how this all works. So, as I said, I explained to you how when we went from points to strings, it took us quite a while to get used to the idea and to understand all of the uniquely stringy things that happen. With the holographic principle, it's now very different from any physical law that we've dealt with before. How does it work in detail? And OK, we kind of understand it for black holes, but how does it work in our expanding space-time? Now, the interior of a black hole, the bit behind the horizon, is a lot like a black hole, a lot like a Big Bang, but in reverse. The space is getting smaller, not bigger, and there's a singularity in the future, not the past. But the interior of a black hole is a lot like a Big Bang in reverse. So understanding how this works inside a black hole, what it says for the inside of a black hole, might be a good place to start. Another question, where exactly did Hawking go wrong? Because Maldaceni's argument that information is not lost is very indirect. It requires that you believe a lot of things. But if you're a skeptic, you can ask, where did he make his mistake? By the way, you know, it might feel as though one is really piling one assumption on another here. And so it's worth emphasizing that these things get checked. So in particular strings, which were invented to solve this problem of Planckian scattering, also turned out to solve the problem of the atomic structure of black holes and the information problem. So when you find something and it solves problems that you didn't expect it to solve or you didn't create it to solve, you have the sense that you're headed in the right direction. Also, this discovery of Maldaceni's, this connection, is a precise mathematical statement that you can test in a precise way. It's not proven, but it's been subject to many, many tests. And so this line of reasoning, at the very least, has led us to a remarkable mathematical result about the theories that we have in physics, gravity and the nuclear forces. And it may be just a mathematical result, but all of the history says that the physics and the mathematics go hand in hand. OK, so we want to take these principles and push them further. And so about a year ago, it would seem like a good time to have one of our KITP programs to revisit Hawking's original paradox, understand discuss where we stood on it, because not everybody agrees, and discuss where we're going. And working with, this is my brilliant young colleague in UCSB physics, Don Marolf, and two grad students, Ahmed Al-Hari and Jamie Sully, we set out to think more clearly about where Hawking went wrong. And there was a list of things which were widely believed. One of them, as I told you, is that information is not lost. One of them is that an observer who stays outside the black hole sees nothing unusual. And the third is that an observer who falls through that horizon into the inside of the black hole sees nothing unusual. Now, what do I mean by nothing unusual? So again, somehow to solve the information problem, information has to travel in some way, has to get in some way from the inside of the black hole where it's fallen to the outside into the radiation. And what was believed was this happens, but it happens in a very subtle way where no single observer sees anything unusual. And what we showed is that these three assumptions are inconsistent. In some ways, the result is not so remarkable. It really is not so different from the reasoning that Hawking used 40 years ago, but just running it backwards and trying to be more precise about it. Actually, it's rather interesting that there are people who are trying to build a computer that uses quantum mechanics in a unique way. In fact, in our physics department and across the way at the nanoscience building. And in the process of thinking about these quantum computers, people have thought more clearly about how information is stored and transferred in quantum mechanics. And so partly influenced by those ideas, we showed that these three widely believed assumptions would imply an impossible quantum state for the Hawking radiation. So we were puzzled by this, but because it was a KIT program, we were surrounded by experts. And we went to them, and none of them could get us unconfused. And so eventually we published a paper, and now we've gotten everybody confused. So if you assume that nothing strange happens outside the horizon, the part that we can see from the outside, then what our argument seems to say is that if you fall into the black hole, you don't actually hit that smooth space that I drew. You hit a sphere of high-energy particles that basically destroys you. And apparently there is no space behind the horizon. Everything I've been drawing, everything we learned from classical general relativity is a lie. And that, of course, is a preposterous-seeming conclusion. Nobody believes it at first, but as with Hawking's original argument, nobody can find a mistake in the reasoning. So something has to give. And in some sense, this is, again, the conflict between quantum mechanics and space-time. Because quantum mechanics seems to say that this is what we get. And space-time, general relativity, seems to say that this is what we get. And so this conflict is still there. We still have this very sharp puzzle where we maybe can figure out how to fit these two theories together. Now, if you've been keeping score, in the previous conflicts, actually, quantum mechanics has always won, and space-time has always lost. But this time, who knows? Maybe space-time will win one. So this is where we are. This is what we're puzzling over. It's a very interesting time. People have lots of ideas. Very quick. I should say a few things about real experiments very quickly, just so you know that we do think about them. So this unexpected connection that Maldacena found between the gravitational force and the nuclear force can be used to think about gravity, but can also be used to understand the nuclear force better. And so there are these collisions of gold nuclei at RIC, the accelerator in New York, and the LHC, which produce a new state of matter, the quark-gluon liquid, which turns out is best described using Maldacena's ideas in terms of a black hole. It can also be used to describe other exotic phases of matter. And I mentioned earlier on that the killer app for all of quantum gravity is understanding the beginning of space and time. We know remarkably already that the pattern, all the structure in the universe, the pattern of the galaxies and then the stars and us even, originally came from quantum mechanics, from quantum fluctuations in the early universe that were magnified by the expansion of the universe. But there are still many mysteries with this, and continuing data. There's going to be a new data release in 2 weeks. Each new data release brings us closer and closer to the Planck time, and closer to where quantum mechanics and gravity come together. So those are places where the things I've talked about might impact real observations. But as you saw with Dirac and with Maxwell, when you set out to answer this kind of question, really the most interesting things that you learn are the things that you didn't expect to learn. And I think that we have more surprises in the future. So thank you.
Thank you so much, Joe. Questions? And wait till I get to the mic too.
Hi. A point along the way was Hawking radiation. I always had a question about it, in particular, if you don't mind, just that one small.
Yes. Oh, want to go back? Yeah.
Okay. Oh, you don't have to go back. Well, yeah. Okay, that's good. Good. I didn't know you could do that.
Yeah.
There we go. Okay. So the black hole itself is not emitting any radiation because nothing can get past the event horizon again. Correct? Correct. That is correct.
Yeah, in a sense, things are popping out just outside the horizon. One's falling in and one's escaping. Yes.
So the way I see it is that the black hole is tearing the vacuum apart.
Very slowly, not dramatically.
Right, of course, very slowly.
Unless the firewall is right, yeah.
Half the energy of that tiny bit of space is going into the black hole, and the other half is being released in some trajectory away from it. So in a sense, the black hole is cooling the vacuum in its vicinity. Yeah. It's not hot, it's cooler.
Well,
so I don't understand that difference.
So when you take any kind of body and heat it up, it emits a characteristic kind of radiation. If you take a piece of metal and put it in a fire and then hold your hand near it, you'll feel actually heat radiation coming off of it, not just convection, but heat radiation. And the radiation that's produced by the black hole has the same kind of spectrum, called a black body spectrum, as the radiation that's produced by a heated object. But not just that, in thermodynamics there are, we have these relations between the change in the entropy, the change in temperature, the change in the energy. And one of the things that was learned in the 70s was that there are the three or four, depending on how you count, laws of thermodynamics. And there are 3 or 4 laws of black hole mechanics. And these are in one-to-one correspondence. They are exactly parallel in structure. And Hawking radiation explains that this parallel structure is not just a parallel structure, it's the same thing. So if you I don't know if that, yeah.
Next question? I saw a hand, yeah.
What's the topology of a firewall?
Good. Same as the topology of a horizon. So the horizon is a sphere, and you can make there are more exotic black holes that have other shapes, but basically in ordinary spaces, the horizon and the firewall are always a sphere. So yeah, it's so I can, because I'm limited to a 2-dimensional slide, I can only draw a circle instead of a sphere. But basically, the space just ends. Well, so nobody, if this is right, no one knows what lies past this. There are ideas of this sort that have been around for longer. There's something called a fuzzball, which, it's interesting. There are equations that go, it's not clear whether it's the right direction, but where, in fact, beyond the firewall there'd be some kind of smooth space. But then there are also notions that what's happened is that the singularity, instead of sticking down here out of sight, has actually migrated outward to where the horizon was. And so it's an actual end of space.
Yeah, you do. Sorry.
The idea that heat is motion replaces the caloric substance theory of heat. And I've always been, obviously a single particle in motion. Does it have a temperature? Is it emitting rate? So, heat is what we sense as heat is correlated with motion, but is it...
Good. No, you're correct. It's disordered motion. It's random motion. Good. No, and no, you're quite right. It's random motion, and here too in the black hole case, it's random motion of these constituents, not correlated motion all in one direction. And again, heat is a property not of single particles, but it's a collective thing that emerges when you have many particles. It's only definable when you have many particles.
Hi. As you were talking about the string in the box,
yes.
You said as the small space goes away,
yes.
The math says a new large space should appear and emerge.
Yes.
does that surprise you? Did you expect that?
Absolutely. No, this was a great surprise. This is a great. This is something that strings do that particles don't do, and it comes out of the mathematics in a rather simple way. But yeah, if you put a particle in a box and make the box smaller and smaller and smaller, the particle is going to be more and more confined. Nothing special is going to happen. Where this comes from, by the way, is the fact that strings can wind. So the box, strings can kind of wind around the box in a way that particles can't. And as the box gets smaller and smaller, it becomes easier and easier for the string to wind because it doesn't have to wind so far. And it's actually that winding that gives rise to the new space. But what happens is, you just look at the spectrum of strings in a box. And it's a pretty simple spectrum. It's just a bunch of harmonic oscillators, things that we're familiar with for a long time. But you look at the formula, and it just has this symmetry between very big boxes and very small boxes. Hard to mistake. For the open strings, again, it's a little more intricate, but you can still figure it out.
Behind door number 1, you have quantum mechanics and no singularity.
Yeah.
And door number 2, you have general relativity but no quantum mechanics. You talked about space-time being emergent. So my question is, do you think there's a more fundamental underlying theory from which this all emerges, or do we have to actually give up one or the other of these theories?
Good. This is something that we puzzle about a lot, because one of the things I mentioned was that Maldacena does give a fundamental description of gravity in the whole space, seemingly in terms of variables that live out here. So in this description, quantum mechanics has survived just fine. But space-time, again, it's coming out of the dynamics. It's not there at the beginning. Only the empty frame is there at the beginning, and kind of the dynamics fills in the space-time. Now, this, again, is a striking discovery. Maldacena's paper is actually the most cited paper, has the most it's been referred to the most times of any paper in the history of my field. Understanding what it means has kept us busy for a very long time. But one of the things that this new train of thought has led to is that maybe it's not as complete a theory as we had thought, and that it's not the fundamental theory of what's happening. We need a more complete theory. And this is one of the things we throw around, but we don't know. We don't have. I don't think we have any really good ideas where to begin with that.
All right. On that note, one final question. It looks like you got to wait. Slow down.
Space and dark energy.
Can you repeat the question?
Is there a question between emergent space and dark energy? So dark energy, in some ways, is not a surprise. I showed you. Sorry, where's my picture? I showed you how empty space is full of stuff happening. This is what you would call zero-point energy, and then there's also energy due to the Higgs field, now discovered. There's energy due to the fields of the strong nuclear force. There's lots of stuff happening in empty space. We don't see it because it's like a fish not being able to see water. It's such a symmetric space that we can only detect these things indirectly. But all of these things have energy, and if you add them up, in fact, there should be a lot more dark energy than there is. The real puzzle is why there is so little. And I don't think it's not so much connected with space being emergent. It's really, dark energy is really a basic property of quantum systems. So I'll just leave it at that.
All right. Thank you very much, Joe.
Yes.
Just to remind everybody, there's refreshments through the door and near the courtyard.